Hi everyone, this is Monica Chism, and I'm going to be talking about an evaluation of the cartographic quality of orthophotos produced with a refined photogrammetric point cloud. So like we all know, orthoimagery is a crucial component to creating GIS data and mapping. It's used as a backdrop for digitizing GIS features and helps to give GIS data context. Map accuracy and visual quality are two of the main factors that make a good orthophoto. Ortho-rectified imagery is an aerial photograph from which distortions from camera tilt and ground relief have been removed. An orthophoto should have the same scale throughout and be able to accurately represent distances on the ground. The accuracy of an orthophoto depends heavily on the accuracy of the orientation data and the quality of the surface data that it's made from. So as mentioned in this study, I'm going to focus on the surface data that goes into the orthophoto production. So Lidar data is typically the best choice for a high-density elevation dataset that can be used to rectify an ortho. But it can also have some drawbacks. Capturing new Lidar data can be expensive. It can also be a tedious process to download existing Lidar data. It's also possible that there just isn't an appropriate current dataset out there for your area of interest. For example, the 3DEP program might be the best dataset in terms of high-quality coverage for the US right now, but it also spans back to 2016, and it's not projected to complete coverage until 2023. So a possible alternative to Lidar is phodar. Phodar's a 3D surface that's derived from imagery. During this process, overlapping light pixels help the software to generate X, Y, and Z values for each pixel. A surface model is created. Phodar's come a long way in the past few years. Many photogrammetry suites have incorporated this capability. Phodar is typically cheaper than collecting new Lidar if you don't have a suitable surface for your ortho project area. You're already going to collect the imagery, so wouldn't it be great if you could generate an automated and accurate surface as well? I've used Inpho's Match 3DX, which was just released last year, to test out this process. Match 3DX uses the semi-global matching algorithm to create a 3D surface model. The benefits of using a product that uses the SGM matching technique are that it can generate up to one elevation point per pixel in the image. It also determines that value by considering neighboring values, and therefore it creates a smoother transition between Z values than in other phodar algorithms. It can also use fewer input images than some techniques, which makes it more suited to produce good results with a traditional aerial imagery flight plan, whereas other types of image matching might require more images, raising the cost of image acquisition due to additional lines of flight. It can also create a point cloud that more closely resembles Lidar. This makes post-processing and filtering more successful than that of a grid-style phodar dataset. This leads me to the project objective. This was to investigate the use of an SGM phodar point cloud for ortho rectification. The goal was to evaluate an SGM phodar-derived orthophoto against one that is Lidar-based. The evaluation was based on the two main factors that make an orthophoto useful: its ability to achieve map accuracy and its ability to be visually appealing. If it can achieve one but not the other, is phodar still a useful method for creating an orthophoto? A map-accurate surface could still create visual defects in the orthoimagery, and it often does. So my goal was to determine whether a phodar-derived, high-resolution orthophoto can be as accurate and appealing as that of a Lidar. So this is the study area. It's the downtown area in the capital city of Kentucky, Frankfort. It contains urban areas, forested areas, and water. This area was chosen for the various terrain types within one dataset, and a recent capture in the spring of 2019. This is also an especially great site because LiDAR and ground control were captured alongside the imagery, and this can be used for a head-to-head comparison with a phodar. The data for this project include 6-inch resolution aerial imagery captured in the spring of 2019 with an UltraCam Mark I large format sensor, a high-quality aero triangulation solution that uses ground control collected between 2014 and 2019, and a 5-foot resolution LiDAR DEM created from QL2 LiDAR that was also acquired in the spring of 2019. To process the data, first I created a phodar point cloud using the SGM technique in Inpho Match 3DX. As mentioned, this process requires the imagery and the aero triangulation solution as inputs. Various settings were tested within the 3DX software, and the best resulting surface, which was a 3D digital terrain model, was the one used for this research. Next, I created a DEM of the unfiltered phodar, which had higher max elevations than the LiDAR. So knowing this might cause defects in the orthophoto, I filtered the phodar point cloud in TerraSolid to better represent bare earth, and then I created a secondary filtered phodar DEM. The process in TerraSolid was fully automated classification, but only after the optimal parameters were tested and determined. So using the revised DEM and the LiDAR DEM, I created 2 sets of orthomosaics to use for comparison. Following the processing of the data, I wanted to see how similar the phodar was to the LiDAR data. I took a random sample of 1,000 points and plotted the corresponding LiDAR and phodar elevations on an XY axis to visualize their similarity. As you might expect, both the unfiltered and the filtered phodar match very closely to those of the LiDAR, but clearly shows that the filtering of the phodar dataset significantly improved its agreement with the LiDAR. Having worked with phodar in the past, I knew these elevation changes were largely due to buildings and vegetation left in the unfiltered phodar DEM. While having these values in the data doesn't significantly alter the accuracy of the phodar itself, it can severely impact the visual quality of the orthophoto. It could create swirly, smeary trees, and other similar distortions. It's safe to say that the filtered dataset is the better of the 2 phodar datasets, so the remaining analysis was done with the filtered phodar dataset. The next round of testing involved creating ortho-rectified mosaic imagery so that I could verify the ortho-horizontal accuracy. Orthophotos were generated for the phodar and for the LiDAR. Known XY values were measured using ground control points overlaid on the orthoimagery, and a difference was calculated. Ground control points were measured against the phodar-based ortho and the LiDAR-based ortho, and the differences were calculated using the ASPRS guidelines for calculating the root mean square error. The RMSE for each dataset is seen here for comparison to each other. The RMSE for each ortho is well under 1 pixel, which is 1/2 of a foot. And the accuracy tested at a 95% confidence level is just over 1 pixel for each dataset, with the phodar having a slight upper hand. This means that with 95% certainty, the error in the phodar and LiDAR datasets is limited to 0.51 feet and 0.52 feet respectively. This demonstrates that the phodar makes a map-accurate orthophoto similar to that of the LiDAR. Next, we'll see how they measure up in terms of visual appeal. Because a huge part of creating a good ortho image is creating a pretty picture, the next analysis performed was to assess the visual quality of the orthos generated from both DEMs. a set of phodar-derived imagery and Lidar-derived imagery was systematically screened, and every part of the photo was examined at a consistent zoom level. This QC method is a typical procedure for ortho production to find visual defects within the imagery. For the purposes of this study, only smears, warped bridges, and other warped features, such as buildings, roads, or retaining walls, were identified, because those are all defects that would likely be caused by the surface. Each defect was recorded within a geodatabase and exported into a table for comparison. The results of the visual inspection showed that both data sets had a similar number of defects. Viewing the LiDAR in orange, you can see that while the overall number of defects in the LiDAR-derived orthophoto is higher than in the phodar-derived orthophoto, the difference is due to a larger number of warped bridges than in the phodar-derived orthophoto. Having said that, overall, the visual quality between the two datasets is so close that the overall effort required to eliminate the defects in the final product is likely about the same. In this slide, you'll see some examples of bridges that were warped in the LiDAR-derived imagery on the top row, but were not warped in the phodar dataset on the bottom row. To conclude, filtering is an important first step to make an ortho-appropriate phodar surface. However, desirable results were achieved with little to no manual effort if the right conditions are met. The LiDAR and phodar DEM elevations were very closely matching post-filtering. The phodar-derived ortho contained 5% fewer bridge defects than the LiDAR-derived. However, overall, they were very similar in number of defects. The phodar-derived ortho accuracy was comparable to that of the LiDAR-derived. So having said all of this, the phodar-based orthophoto performed as well or better than the Lidar-based orthophoto in testing of accuracy and visual appeal, making it a potential cost-effective alternative to LiDAR. So I wanted to end my presentation with a few things to consider. First, these tests were performed with one dataset, and other terrain types, ground cover, or resolutions will likely yield different results. Also, the phodar surface did end up with a comparable number of defects to that of the LiDAR. This was with a fully automated classification method. Even better results may be achieved with a more manual approach, such as adding break lines to the process or performing manual ground edits, which we did not do in this study. And similarly, other datasets might require these manual processes to even get similar results. I would like to say thank you to everyone who supported me through this project. Your guidance and expertise is very much appreciated. I also want to say thank you to the NACIS team for having me, and thanks everybody for watching.